So today we're gonna work on this worksheet 5 about curve sketching. We have two problems here, and in each problem the function and the derivative, second derivative, are already given, and we just need to find the following informations: domain, x, y-intercept, and HAVA, and then do those critical number stuff, and then we sketch the graph. So let's take a look at this problem 1. Firstly, this is a rational function, but because the denominator here is never 0, right? It's x squared plus 1 is always greater than 0, so the domain is all the real numbers. And now we take a look at the y-intercept. The y-intercept is when x equal to 0, right? Y-intercept, you let x equal to 0, right? We have g0 equal to 0 over 0 squared plus 1, which is 0, right? So y-intercept is 0. And x-intercept is when y equal to 0. So let y equal to 0. That is gx equal to 0, right? It implies that x divided by x squared plus 1 is equal to 0. And it means the numerator is equal to 0, so x is equal to 0. So you see that both the x-intercept and y-intercept are 0, which means the function passes through the origin. Now let's take a look at horizontal asymptote and the vertical asymptote. Horizontal asymptote, we let this limit x approach positive infinity, and then we have 1 over divide the top and the bottom by x squared, so this is 1 over x, and the bottom becomes 1 over 1 plus x squared, right? This is equal to 0. And the same thing is true for negative infinity. This is also 0. Okay. So now we can conclude that HA y equal to 0 is LHA is a horizontal asymptote. And now we take a look at the vertical asymptotes, right? In this question and in this function, there's no vertical asymptote, because vertical asymptotes only occur when the function is not defined. But we see that the function is defined everywhere because the domain is all the real numbers. So there's no vertical asymptotes. No vertical asymptotes. So that's very straightforward for these basic informations. And now let's take a look at critical numbers. Okay, critical numbers, we're gonna take a look at the derivative. The derivative is this one, right? Gx equal to this. So this derivative always exists because the denominator is never 0, which is same as the function. So we only have the that type of critical number where the derivative is equal to 0, right? So you let this equal to 0, and then we have 1 minus x squared equal to 0, which shows that x is equal to positive and negative 1, right? These are the critical numbers. And then we're gonna draw our number line. one here and positive one here, right? And then we're going to test the derivative, the sign of the derivative. For example, we choose a number that is less than -1. We check this g prime to -2. Right? This is equal to -3/25, which is less than 0. So you have minus sign here. So the function is decreasing, right? And then you choose another point, maybe g prime 0. G prime 0 is greater than 0 because it's equal to 1. So we have a positive sign here, right? Function is increasing. And you choose the last point, maybe g prime 2, that is -3/25. It's also a negative, so negative sign here. Function is decreasing, right? So now we have the intervals of decrease and increase, right? This is increasing on from -1 to 1, decreasing, decreasing, on this from -infinity to -1, and 1 to positive infinity. Okay. And now let's look at the location of the local max and local min. Right, the function is decreasing here and then increasing here. So at this place there will be a min, right? Local min is here, and local max is here, right? So now we have the local min. It's g -1, that is equal to plug in -1 to the function, gx is here, that is -1 over 1 plus 1, that is -1 over 2, okay? And local max, that is g1, right? That's 1 over 2, okay? So that is part B. And now let's move on to the next part. Find the following properties of the g of x in intervals of concave up and concave down. So we're going to take a look at the second derivative here. Okay. And then we'll let this equal to 0. Right? And since the fraction equal to 0 means numerator is equal to 0, so we have this equal to 0, right? Which means x is equal to 0 or x squared is equal to 3. So we have x equal to 0 or x equal to negative square root of 3. Okay, and then we're gonna draw a number line. Put these numbers onto the number line. Negative square root of 3, 0, and positive square root of 3. And then we're going to test the sign of the second derivative. So you see that in here, this x is going to be negative, and this x squared minus 3 is going to be positive, right? So we have a negative sign here. or you can just plug in 3 prime 2. You see that is negative. And then the next point, you're gonna plug in a negative 1 here, okay, negative 1. See that the x here is positive, negative, and this one is also negative, right? So this is positive, this plus sign, okay. And next we're gonna plug in g2 prime 1, right? Similarly, this is gonna be positive. This should be negative, because this part is negative, while this part is positive. The x is positive. And finally, we plug in this g2 and see that that is gonna be positive. Okay, so this is negative, positive. And then we have concave down, concave up, concave down, and concave up. Just like that. Okay. So concave up on the interval from negative square root of 3 to 0, and also positive square root of 3 to infinity, and concave down at this from negative infinity to negative square root of 3, as well as from 0 to square root of 3. So those are the concave up and down intervals. And then we're going to take a look at our inflection points. Inflection points occur when the concavity changes. So concavity changes from concave down to concave up. So there is an inflection point here, right? And also inflection point here, right? Changes from concave up to concave down, and also here, right? So inflection points. It's this negative square root of 3, g negative square root of 3. And then 0, g 0, right? And also square root of 3, g square root of 3. Okay, so that is this one. So now we have everything ready. We can just sketch this function. Okay, sketch the function. So we know that the function passes through the origin. Okay, so it's here, and then it has the 0 as our horizontal asymptote, and the local max is gonna be this point, that is 1 over 2, and local min is, so it should be here, 1 negative 2, 1 is here. Oh no, let's say it's here, because this is gonna be 1, right? This is gonna be 2, 3, 4, 5, like that, negative 1, negative 2. And then local min is gonna be negative 1, negative 1 over 2. So it's here. Negative 1 over 2, right? And then we know the function is increasing from negative 1 to 1, right? So just connect this. And now from 1 to positive infinity, the function is going to be decreasing. So it's like that. And it will approach the horizontal asymptote, which is the x-axis. And for the other end, that is going to be decreasing, right? So it's decreasing from here, right? And we know that y equal to 0 is the horizontal asymptote. So it approaches the x-axis, also at the left-hand side. So that is the sketch of this graph. We also need to locate the inflection points. Inflection point, one is here, right? G0, that is 0, G0, right? And also another point is square root of 3, that is about here, right? Square root of 3, G square root of 3. And the other one that is here, that is negative square root of 3, G negative square root of 3. Okay? So now we have the sketch of this function. This is a simple question. Okay? And now things should be clear, and we can move on to the next one. The next one we have function, also a rational function, right? And then we will do it the same way. Find the domain first. We know denominator cannot be 0, right? So this denominator can be factored as s minus 2 x plus 3, right? This is not 0, which means that x is not 2, not negative 3, right? So we exclude those numbers. Domain is going to be from negative infinity to negative 3, and negative 3 to 2, and 2 to positive infinity, just excluding these two numbers. And then y-intercept. For y-intercept, we let x equal to 0, right? We have g0. Oh, sorry, in this question should be f equal to 0, right? Y-intercept is 0. And for x-intercept, we let y equal to 0, so fx is equal to 0, right? Which implies this thing equal to 0, right? And now we have numerator equal to 0, which is negative x squared minus x equal to 0. And then we have the x times negative x, x plus 1 equal to 0. So we have x equal to 1, or negative 1, or x equal to 0, right? So it has two x-intercepts, that is negative 1 and 0. And now we find the horizontal asymptotes. So we look at this limit, positive infinity, negative x squared divided by x squared plus this minus 6, which is equal to, divide the top and the bottom by x squared, so we have negative 1 minus 1 over x. This is 1 plus 1 over x minus 6 over x squared, right? And becomes negative 1. And then we do the other one, negative infinity. And you will find that it's the same, also negative 1, right? From here we conclude that y equal to negative 1. It's a HA, horizontal asymptote. Now we take a look at the vertical asymptotes. So vertical asymptotes, notice that they only occur when the function is not defined. A function is not defined. We know that the function is defined everywhere except for these 2 points, right? fx is not defined. So we will check limit x goes to 2 and 3 from the left and from the right. So from the right first, that is going to be negative x squared minus x divided by x squared plus x minus 6. All right. And then we replace the denominator by that factorization, that is x minus 2, x plus 3. Right. Plug in the top, we have the top we have negative 6, and the bottom we will have 0 plus, because when x is greater than 2, just slightly greater than 2, this factor is going to be greater than 0, but this factor is going to be also greater than 0. So both are greater than 0. So this is 0 plus, right, which is negative infinity. Right? And they check the other one. Similarly, this one is going to be positive infinity, because that is negative 6, 0 minus positive infinity. And then you check the other two in a similar way. Running out of space here, that is hard to write. Similarly, you have this 3 plus approaches 3, right? So it's going to be also negative 6. We say negative 6. 3, that is not negative 6. It should be a negative 3 squared, a negative 12. But anyway, it's not important. It's negative, right? Negative, and this is gonna be 0. Oh, sorry, approaches negative 3, not positive 3. Approaches negative 3. Approaches negative 3, that is gonna be also negative 6. And since it's greater than negative 3, so this one is gonna be greater than 0, right? But this one is less than 0. So it's going to be 0 minus, and then we have positive infinity. And for the other one, we will have negative 6 by 0 plus, right? That is negative infinity. Okay. Just take a look at the sign here. Also forgot this negative sign. It's a negative 3, not positive 3. Take a look at the sign here. The sign here is negative because it's less than negative 3. And this one, that is also negative. Okay. So now we have the vertical asymptotes, VA. They are x equal to 2 and x equal to negative 3. 2 vertical asymptotes. And after that, we're going to find critical numbers. So we're going to take a look at the first derivative. And let this equal to 0. So we have 2x plus 1 equal to 0. which is 2x plus 1 equal to 0. X is equal to negative 1 over 2, right? And that is when the derivative is equal to 0. And also we need to consider when the derivative does not exist, right? That is when the denominator equal to 0. So we will have x equal to 2 and x equal to negative 3. But these are not the critical numbers because they're not inside our domain, right? So this is the only critical number. Only critical number. And after that, we're gonna draw our number line and place all these numbers on the number line. Negative 1 over 2. And also these 2 points that is not in our domain. So that is 2 and this is negative 3. We also need them. And then we're gonna check the derivative, the sign of the derivative. We see that there is a square in the denominator, so denominator is always greater than 0, right? And on the right hand side of negative 1 over 2, the numerator is going to be greater than 0, so it's going to have plus sign here, and negative sign here, negative sign here. It's like that. You can also plug in a number to test it. For example, you plug in f0, right? See that this is greater than 0. Plug in f prime 1 is greater than 0. Plug in f prime negative 1 less than 0. Right? F prime, like for example negative 4 is also less than 0. So now we have decreasing, decreasing, and increasing, increasing. Okay, so intervals of increase, that is increasing on this negative 1 over 2 to 2, and also from 2 to infinity, and decreasing on this negative infinity to negative 3, as well as from negative 3 to negative 1 over 2. So these are the increasing, decreasing intervals. And now we can find the concave up, concave down intervals by using the second derivative. Okay, let this equal to 0, and we have numerator being 0. So we have this 3 equal to 0. And we try to solve this equation. But the note here says that this thing is going to be always less than 0, right? For all values of x. Right? So that means our second derivative can never be 0. So we can't just use this method to solve it. Right? It's never 0. But we're still able to determine the sign of the second derivative by using the number line. So just draw the number line directly. And there's no point such that second derivative is equal to 0, but we are allowed to place the negative 3 and 2, which is not in our domain, these 2 points on the number line, right? And we're gonna test the sign of the second derivative. Okay, second derivative. So we know that the second derivative always has the negative numerator, as is in the note, right? So numerator is negative, we only need to take a look at the sign of the denominator. So the sign of the denominator depends on the sign of this x squared plus x minus 6. Right? So this thing is actually a negative 12 3x squared plus 3x plus 7 divided by x plus 3 x minus 2 to the 3. Right? Okay, we know that at here is going to be greater than 0 because both x minus 2 and x plus 3 are greater than 0. So we will have a positive sign here, right? And now this is in between we're gonna have x minus 2 less than 0, but x plus 2 greater than 0. For example, if you test plug in like 1 in the denominator, you will get a negative value here, right? So it's negative. Oh, I also forgot. I need to consider the sign of the numerator. Numerator is gonna be negative, so here is negative, right? Denominator being positive, but numerator is negative, so it's negative here. So maybe we plug in a point to test, just for example 3, right? So plug in this, that is negative 43 divided by 18 less than 0, right? So concave down here, and then in between, that is going to be negative in the numerator and negative in the denominator, so it's positive, right? Concave up here. For example, you can plug in 0, right? That's going to give you 7 divided by 18 greater than 0. And finally, we test here. That is when both brackets less than 0, so we should have negative, both bracket being negative, so we should have a positive in the denominator and then negative in the numerator, so that is going to give us negative sign here. For example, you can plug in f2 prime negative 4, that's going to give you negative 43 divided by 18 less than 0. So it's going to be concave down here, right? So now we have our concave up intervals, that is from negative 3 to 2, and our concave down intervals is going to be from negative infinity to negative 3 and 2 to positive infinity. Okay. And of course, we need to consider the inflection points. Right? Inflection points is when the concavity changes from negative to positive, from positive to negative. So we were supposed to have negative 3 and 2 as our inflection points. However, these 2 points, they're not in the domain of the function, right? So there's no inflection points because negative 3 and 2 are not in the domain. Okay, so that saves us from finding them. Okay, so that is all about this question, and we should just finally graph it here. We notice that we have 2 x-intercepts. That is the when x is equal to negative 1, that is here, right? Here is negative 1, right? This is negative 1, 0. And also here, right, that is 0, 0. That is two x-intercepts. And 0, 0 is also going to be our y-intercept. Okay. And we forgot to find the local main, right? Local main. The local main should be here. At this place, right? The local main, that is f negative f of negative 1 over 2, that is equal to negative 1 over 25. Okay, that is when the derivative changes from negative to positive. And then we locate it here, negative 1 over 2. That's kind of in between here. So this is going to be negative 1 over 2, negative 1 over 25, local main. Okay, and we have our vertical asymptotes, that is x equal to negative 3, right? Negative 3 is here. So this x equal to a vertical asymptote. And also another vertical asymptote, that is x equal to 2. X equal to 2. Okay. And our horizontal asymptote, that is y equal to negative 1. That's here. And now we can graph our function, right? The function is going to be decreasing from negative infinity to negative 3. And so it's going to be like that, right? And when x approaches negative 3 from the from the left side, it's going to approach negative infinity. So it goes down like this, right? And from the other side, it's going to be positive infinity, right? And it's still decreasing, right? Still decreasing, so it's decreasing from here, right? And it will be gonna touch this point, right? Our vertical, the x-intercepts, and then it continue to decrease until it reaches this point, the local mean here, and then it stops, right? And from negative 1 over 2 to 2 is going to be increasing, right? Increasing here, and then touch this point, and then it goes to infinity. Okay, and then it continues to increase from the other side, that is from this side, and then increase again until it gets very close to the horizontal asymptote. So it's like that. Okay. So that is our rough sketch, and there's no, no inflection points for this function. So that's all of the curve sketching, and also very straightforward. So I think that is all for today, and I will see if you have any questions. Any questions?